When we hear the keyword teleportation, we often think of miraculous technologies that can instantly transport matter from one place to another at the push of a button. This concept, popularized by shows like Star Trek, seems straight out of science fiction, where characters can beam up or beam down with incredible ease. However, as fascinating as this concept is, teleportation in its true scientific form is not about transporting physical objects or people in the way we imagine. It is, in fact, the transfer of quantum information. Quantum teleportation involves the transfer of quantum states, like the spin of an atom, from one particle to another, regardless of the distance between them. This groundbreaking phenomenon has already been successfully demonstrated in experiments around the world, proving that the science behind it is no longer just a futuristic idea. Rather, it is a present reality. For example, scientists at the Max Planck Institute for Quantum Optics recently developed a method for teleporting quantum information using a single photon as a resource. This simple but powerful technique opens up new possibilities in quantum computing and communication. Similarly, Chinese researchers have demonstrated a quantum link between two ground stations 200 kilometers apart, using satellite technology to transmit entangled photons across vast distances. While quantum teleportation doesn't involve the transfer of physical matter, it shows great promise for transmitting information across immense distances without delay. This concept harkens back to the work of two of the most prominent figures in quantum theory, Albert Einstein and Niels Bohr. Though they were friends, their relationship was also marked by intense debates about the nature of the quantum world. One of their major points of contention was the concept of entanglement. Bohr argued that entangled particles could maintain a shared quantum state, no matter how far apart they were. In other words, changes made to one particle would instantaneously affect the other. Einstein, on the other hand, believed that any change in one particle would require a signal to travel between the particles, which he argued could not happen faster than the speed of light. This disagreement culminated in Einstein's famous dismissal of quantum entanglement as spooky action. At a distance, he was skeptical that particles could communicate instantaneously, a concept that seemed to defy the established laws of physics. However, as experiments in the following decades have demonstrated, Einstein's skepticism was misguided. Over time, numerous experiments have confirmed that quantum entanglement is a real phenomenon, and particles can indeed remain connected in a non-local way, independent of distance. One of the most groundbreaking of these experiments came from China, where physicists demonstrated the ability to send entangled photons via satellite over 200 kilometers. This achievement marked a major milestone in the field of quantum communication. The experiment's success hinged on the fact that the photons traveled through space, where they were less likely to be disturbed by the atmosphere or other earthly barriers. On the ground, researchers had to account for challenges such as the high speed of the moving satellite and the potential loss of entangled photons as they passed through Earth's atmosphere. Despite these obstacles, the satellite succeeded in sending entangled photons to two ground stations, creating the world's first orbital quantum network. This accomplishment opens up exciting possibilities for future quantum communications and secure information transfer. Yet, even as quantum teleportation experiments advance, it's important to note that this phenomenon comes with significant limitations. For example, only a small amount of quantum information can be transmitted at any given time. Typically, this means just a few bits of data, making quantum teleportation less suited for transmitting large volumes of information, such as the details required to transport complex objects, or, as Star Trek envisioned, human beings. Moreover, quantum teleportation is highly dependent on the infrastructure in place at both the sending and receiving locations. For teleportation to work, the particles involved must be entangled in advance and maintained in a stable quantum state. This presents a substantial challenge when it comes to large-scale teleportation. If we were to beam a human from one location to another, the process would require the prior entanglement of all the person's atoms and quantum states, which would need to be carefully transferred without error. The complexity of this task is further compounded by the fact that human beings are not purely quantum systems. Our atoms and molecules are subject to constant interactions with the environment, which can easily disturb their quantum states and cause entanglements to collapse. This makes it practically impossible to maintain the quantum coherence needed for teleportation outside of a tightly controlled laboratory environment. In addition, the sheer computational power required to perform such teleportation is staggering. The technology to scan and process the quantum information of an entire human body would require enormous computational resources, far beyond anything available today. This would include harnessing computational power that exceeds the current capabilities of modern supercomputers, making the idea of beaming people from place to place seem even more far-fetched. But that's not all. The energy demands for such an undertaking would be astronomical. To teleport even a small object, the energy required could dwarf the total energy consumption of entire nations. In fact, the energy requirements might well exceed the amount available on the planet at this point in time. In light of these challenges, the dream of quantum teleportation as seen in popular science fiction is far from reality, at least for now. While the transfer of quantum information over long distances via quantum entanglement is an exciting and promising technology, it will be many decades, if not centuries, before we can even begin to think about teleporting matter or more, specifically people. Ultimately, this research has enormous potential for creating a secure and rapid method of communication across vast distances. In fact, the breakthroughs already achieved in quantum communication have opened up possibilities for a new era of data transmission. We may one day use quantum networks to transmit encrypted information that is immune to eavesdropping, revolutionizing industries ranging from finance to defense. So while human teleportation remains a distant dream, the advances made in quantum teleportation show us that the science behind these technologies is already very much alive and progressing. As we continue to push the boundaries of quantum mechanics, it is thrilling to imagine what the future holds. Will teleportation one day become a reality? While it's still uncertain, the rapid pace of quantum research makes anything possible, and perhaps one day we'll see technological advances that today seem impossible. But for now, we'll have to settle for appreciating the incredible steps forward in our understanding of the quantum world and its applications in communication and computing.